So in this video, I want to discuss high order derivatives or higher order derivatives. So usually we've so far talked about, if f prime of x. So if we have some f of x and we want to take the derivative of it, well, that's just f prime of x, and we can use our tools that we've established, such as the chain rule, and product rule, power rule, etc., to take the derivative of something. Now, what if we want to take the double derivative, which is essentially what higher order derivative means? So what if we want to take f double prime of x? And there are many notations for this. Another notation for derivative is, so if we have f of x, we can say that it's df of x dx, or in this case, d squared f of x dx squared. And this is Leibniz notation, and this is, I believe, Newton's notation probably. I'm not 100% sure, but this notation is pretty convenient. So what do we do if we want to take the second derivative? Well, it's pretty simple. Essentially what we do is we just take the derivative of the derivative function. So let's just start, honestly. I'll explain it with an example. It's the best way to go. So let's say we have f of x. Again, I keep using x to the third, but I think it's a great function to use, especially to take simple derivatives. Well, we already know f prime of x is 3x squared if we use the power rule. And if you forget how to use the power rule, just watch the power rule video. So now if we want to know f double prime of x, which is the second derivative of this function, then we just take the derivative of the derivative function. So in this case, again, we use the power rule, so it becomes 6x to the 1, or just 6x. Now, what if we want to take the third derivative? Well, we can easily do that. We just take the derivative of the derivative function. So, or in other words, we take the derivative of the second derivative function. So the derivative of 6x, well, that's just 6. And what if we want to take the fourth derivative? Well, might as well take the fourth derivative. Well, now we just take the derivative of the third derivative function, which is just 0. And if you wanted to keep going, you just keep getting 0 from here. So we just found the first derivative, second derivative, third derivative, and fourth derivative of this specific function. All right, well, let's do a little more practice. I'll go right here. Let's take the derivative. Let's take a few derivatives of a. If I keep saying the word derivative, it's kind of tongue twister. But let's say we have f of x is equal to sine of x. So if we want to take the first derivative, again, we know that's cosine of x. What if we want to take the second derivative? Well, now we just pretend like our function was originally cosine of x, and we take the derivative of that, and that's negative sine of x. All right, let's take the third derivative. And for trig functions, you can actually take an infinite amount of derivatives, and you're going to keep getting a function. You're never going to get 0, so it's pretty cool. Now the third derivative is the derivative of the negative sine of x. Well, that's just negative cosine of x. And then the fourth derivative. This is just fun at this point. I'm sure you get the point, but let's do a couple more. This is just sine of x. And then notice how it just goes back to what it was. So the fourth derivative of a sine of x is actually just sine of x. So that's pretty creepy. And now if we keep going, we actually just notice a pattern that repeats itself. So if we take the fifth derivative, we get this again. 6 is this, 7th is this, and then 8th is this. So maybe the pattern is anything that's divisible by 4 might be the original function itself for trig functions. I don't know. You can find that pattern. Let's see. And what else? And let me discuss real quick what it represents. We're going to discuss this more in detail as well. But I want to discuss what higher order derivatives represent a little bit, at least in this video. So let's just start with our x to the third function, which, again, I keep using this, but I do think it's a great function to use to explain any of these derivatives. So let's draw it out. We have f of x equals x to the third. Oh, I went through the origin the first try. That's good. So this is f of x is equal to x to the third. So we know that the derivative of that gives us the slope at any given point of the tangent line. And if you don't know that, I encourage you to watch our intro videos for derivatives, and it's very clearly explained. Now, what the second derivative does is, let's discuss this really quickly. So what this does, it gives us a rate of change quantitatively of this function at any given point. So you could probably guess what the second derivative does. What the second derivative does is it gives us the rate of change of the rate of change, or in other words, the double rate of change of the regular function. So we know how fast how fast the rate of change is changing. So that might be a little weird, but let me give you an example, a physical example that makes more sense. So let's just say f of x in this case is position. This is the position of someone. So x-axis is time, and then the f of x-axis is the position. So the rate of change of position is the change in position over change in time, right? And that's just speed, right? How fast you're changing your position is how fast you're going, which is defined to be speed. Now, if you know a little bit of physics, and even if you don't, this might still make sense. The rate of change of speed, which is the second rate of change of position, is acceleration. That means how fast are you speeding up? So how fast is your speed changing? So in other words, let's say you're in a car. If you're in a car, you're moving this way with a speed of 50 miles per hour, and you start accelerating and you get to 70 miles per hour. Your position function is changing, obviously. Your speed function is changing as well. It went from 50 to 70, and you're accelerating. So the rate of change of your speed is changing. And so that's an example of where we can use second derivative.